We're about to get started. Hopefully you can see the slide which is on the screen at the moment. Just a few reminders before we do get started. If you could just keep your cameras off and microphones on mute during the session, that would be helpful. We will have time for questions as we go through, and some of those will come through the chat window. Some of them will be verbal questions as well. If you do have questions as we're going along, please type them into the chat window and we'll do our best to get back to you. And also, if you are having some technical challenges with the webinar, please let us know and we'll try to address those as well. And the other point is we will be recording this, so essentially any audio or video is recorded, as is any content that you type into the chat window, whether it's the public or the private chat as well. All right. So just before we get started, I do want to acknowledge the Earth Observation Australia office, particularly Larissa Marfan, Sylvia Michael and Joe Edkins for getting the webinar up and going for this week, and also our presenters that we have this week, which will all be on Imaging Radar. So Dr. Amy Parker, Greg Madden, and Professor Lyndon G as well. All right, so we might actually get started. So again, welcome everyone. My name's Stuart Finn. I'm based at the University of Queensland. I'm currently the Director President of Earth Observation Australia Incorporated, which is the group putting on these webinars. Dr. Amy Parker, who's talking today, is the Vice President of Earth Observation Australia Incorporated as well. Right. So before we get started, I do want to acknowledge the traditional owners of the land and waters on where we are meeting across Australia. I do want to recognise that as a very broad group of people, and it's important that we pay respect to their elders past and present, recognise their current generation and the emerging leaders there, and also note that we're committed to working with these groups to blending the approaches that we take to understanding the environment and how to look after it and how to build better societies and communities. So here's I guess an outline of today. I'll just repeat the basic housekeeping. So if you could please keep your microphones and cameras off for the moment. We will have time for discussion a little bit later on. If you do have any questions, type them into the chat and we will try to respond to them as we go through this. Just looking through the number of people who are online at the moment, we've got a broad group of people from across Australia. It looks like almost all states and territories. Also people across government agencies from state to Commonwealth. We've got private industry. It also looks like we've got universities and research organisations in there as well as a number of people from defence as well. So that's a really nice diverse mix. It's really important because that's what Earth Observation Australia is about, is bringing everyone together in that particular space. So just a little bit of background before I introduce our presenters and what we're going to cover today. One of the things that we try to do in Earth Observation Australia is present overviews of what's happening in terms of technological developments, whether it's access to different satellite image data sources, look at advances in processing for turning that or those data streams into information, and how people are using that in government and industry and commodifying it and moving forward. And also how we're building our community and moving forwards with education as well. So today we're actually going to focus on a couple of those areas, but specifically around imaging radar. So I think a number of you have worked with imaging radar already. I think from a historic point of view, it's probably our most underutilised data source for a whole range of reasons. I think as you're going to hear from our presenters today, we are moving into a very different era of being able to access imaging radar data sets at a range of spatial resolutions, a range of temporal resolutions, and moving to the point that we've gotten to with optical imaging systems, where we can start to build products and services, and be enabled to work across environments which might be traditionally challenging due to smoke and clouds for optical imagery, or start to look at more detailed and new measurements, whether we're looking at land surfaces, vegetation, ocean surfaces, and how they're changing. Australia has a good background in the applications area here, and it's something we really can build to strengthen what we're doing in our government, industry, and defence applications. And it's an area we need to build a lot more research to applications. We've got private industry working in this area already, but there's also room for a lot more. So it's very exciting that we're able to present this today, and it's sort of a follow-on from some earlier discussions that we actually had about a year ago in this area. So we'll go through several presentations, and then we'll have time for a discussion with our presenters. So again, if you've got questions, type them into the chat window and we'll try and come back to them, or we'll deal with them in that particular session. So without further ado, we'll move on to the first presentation, which is going to be from Dr. Amy Parker at CSIRO. Amy's going to be talking about Australia's national imaging radar facility for the Novasar satellite. I'll just do a brief introduction, Amy, then we can switch over to your screen. Actually, I might stop sharing my screen, Amy, and then you can start to add yours in. Cool. So I'll just do an introduction while Amy begins to share her screen. So Amy is currently the Satellite Operations and Data Manager at CSIRO's Centre for Earth Observation. She manages the Novasar-1 National Research Facility, which includes Australia's requirements for tasking the satellite, downlinking data, data processing and distribution. Amy also leads the Synthetic Aperture Radar Science Initiative under the CSIRO Space Technology Future Sciences platform. She is an imaging radar, interferometric imaging radar specialist, and who's worked with Geoscience Australia and Curtin University. And she also holds an Australian Research Council Discovery Early Career Research Fellowship. So I think Amy's in a very prime role to push this area forward, and I'm really grateful that we're able to have a talk today. And I also do want to acknowledge that Amy's Vice President of Earth Observation Australia. So Amy, over to you.
Great, thanks Stuart, and thanks everybody for joining today. Good morning, good afternoon. I wanted to take this opportunity to really introduce the community to the Novasar National Facility, which will be open for public use and public access to the data by the end of this year. So first, I thought it would be useful to take 30 seconds or so just to review some of the key concepts around synthetic aperture radar, and whether you're not so familiar with this as a source of remote sensing data. So SAR is a form of active remote sensing, which means that it transmits its own source of energy of a specific wavelength and polarization, and then it receives this backscattered response, also at a specific polarization, recording both the amplitude and the phase of the return signal. So that received signal provides information about the dielectric properties and also the structure or the roughness of scatterers on the ground. And in general, you can think of it as the sensor seeing objects or being sensitive to objects that are about the same size as the radar wavelength or greater. So some key capabilities of SAR sensors that are different to optical remote sensing are that it provides penetration through clouds and smoke. And because we're not relying on the illumination of the sun, we can acquire data both day and night. SAR can also penetrate the vegetation canopy to a degree that's dependent upon the wavelength. And it can also provide information about ground displacements through this phase component, because the phase of the return signal is dependent upon the distance between the sensor and the ground. And I think the speakers following on from me are going to talk to you about that in a bit more detail. So why SAR and why now? So Stuart alluded to a couple of these points. In the past decades, the availability of synthetic aperture radar imagery over Australia has been a little bit limited, but really with the ESA Copernicus mission, we now have a source of systematic, free, open access data over the whole country for the first time. And you can see the difference in coverage here between ENVISAT and Sentinel, and the fact that we're really building up a significant archive of C-band data. There have also been some improvements in the accessibility of SAR data and the processing tools available. And all in all, this means that we're really seeing there's an untapped potential for SAR to contribute to the way that we look at our environments and our resources. There are also multiple upcoming SAR missions planned by major space agencies. And these are all unique sensors operating in different wavelengths with different characteristics. And it really means that the volume and the variety of available SAR data is going to continue to increase. So we need to begin to start using it in our applications more extensively. So one of these newly operational SAR missions is NOVASAR. And this is an experimental low-cost satellite mission that was developed and is now operated by a company in the UK called Surrey Satellite Technology Limited. And the intention is to provide a new source of low-cost satellite SAR imagery. So CSIRO, on behalf of Australia, have secured a 10% share of the acquisition and tasking capacity of this satellite. So the investment provides an opportunity really for a step change in our use of SAR data and in our experience of satellite operations as well. So not just in our kind of downstream use of the data, but more in the upstream gaining familiarity with satellite operations. Some key objectives for Australia becoming involved in this mission are really to gain this experience in satellite operations and tasking, because now we're able to task data where we need it most. We're also, for the first time, able to downlink that data directly to Australia for accessing closer to near real time, with the intention that this will benefit time-sensitive applications, looking at things like flooding, bushfires. We're also using it as an opportunity to build new capabilities and new expertise in SAR data to stimulate new applications research. We're able to carry out R&D using this new concept low-cost SAR satellite, and also carry out R&D using a unique payload. And I'll talk to you a little bit more about this unique payload later on. The partnership is also an opportunity to grow our national and international networks. And then looking to the longer term, it constitutes a possible pathfinder towards a full-scale national satellite constellation. The satellite was launched in September 2018, and since this time it's undergone a period of commissioning and operational testing. Last year in December, nominal operations then began, and we have been acquiring data regularly and with more confidence since this time. The national facility for Australia will then open before the end of this year. So if we look here at some of the mission characteristics, I'll highlight some of the key things in this table for you. Firstly, the satellite mission has a life of 7 years. The satellite itself weighs less than 500 kilograms, so it's classed as what we would call a small satellite. So it's quite significantly smaller than platforms such as Sentinel-1. It resides in a sun-synchronous orbit, but a critical point to note here is that that orbit is not fixed. It has a slight drift. And this means that opportunities for interferometric applications will be ad hoc throughout the mission life. So moving on to look at the payload, NOVASAR has a dual payload on board. The primary payload is an S-band synthetic aperture radar that was designed by Airbus. And if we look at some other operational SAR satellites on the electromagnetic spectrum here, you can see that NOVASAR is the only S-band SAR in operation. And this is a little bit like adding a new spectral band to optical imagery. S-band is a relatively unexplored frequency for SAR satellites, and we're really interested in what new information this can deliver, particularly looking at things like vegetation monitoring and forestry monitoring applications. The SAR operates in a number of different acquisition modes, and these can be classed into the 4 key categories that you can see here. Strip map, which is the highest resolution, most useful for detailed observations, through ScanSAR and ScanSAR wide, which are more suited to monitoring over larger areas. And then this maritime mode, which has quite a large swath of 400 kilometers and is specifically designed for ship detection. So each of these modes can be operated with the antenna pointing right or left and from an ascending or descending orbit. Some of the modes also have dual or tripolarization options. And what's been quite exciting for us is that there's actually flexibility to design and implement new modes throughout the mission life. And CSIRO have already expanded the number of operational modes that are available, adding in polarizations, resolutions, etc., to suit to what we think Australia's needs will be. So the secondary payload on board is something called an automatic identification system, or AIS receiver. So AIS is a very high frequency system designed for the automated location and tracking of shipping vessels. So the AIS receiver on board detects signals that are transmitted by transceivers that are fitted on certain types of ships. So this includes all international voyaging ships with a gross tonnage over 300 tons and all passenger ships. Combined with the maritime acquisition mode of the SAR, this is a powerful tool for maritime surveillance. As you can see in this example here, it's possible to detect ships in the SAR imagery, shown by the blue diamonds, that are not sharing their location information via AIS, which is shown by the yellow rectangles. And these may be identified as suspicious targets. One of the unique things about the Novasar mission is that it's actually an international partnership. And this is a partnership between Australia, the UK, India, and the Philippines. Each of these mission partners has fractional ownership of the satellite capacity. So at the moment, our capacity share is 10%. This means that we can request data anywhere in the world, but we have priority over the acquisitions that fall in this area of access that you can see shown by the yellow line. And you can see each of the areas of access for each of the mission partners in these images here. So it also means that we're very unlikely to be able to facilitate acquisitions over the areas of access of other mission partners. So we will unlikely be collecting data over the UK, over India, or over the Philippines, but we can request data anywhere else in the world. So our 10% capacity share in the mission is being operated by what we call a national facility for research. And this is really a natural extension of CSIRO's operation of other long-standing national facilities, including the Australia Telescope National Facility and the Marine National Facility, which you can see here in these circles. And some of the key features of a national facility include the provision of all of the data, free and open access. We will be awarding imaging time on a merit basis, and we have also appointed an independent steering committee to govern operations of the facility. And these are features of other national facilities run by CSIRO. We will also be leading a program of science activities around the use of Novasar data with national and international collaborators. And I'll talk to you a little bit more about that at the end. So the day-to-day operations of the facility follow this simplified flowchart. CSIRO's key daily task is to undertake mission planning, and those mission plans are then submitted to the satellite operator, SSTL, who then arbitrate the requests from all of the mission partners and generate a schedule that's uploaded to the satellite. The downlinking of the data is soon to occur via an Australian ground station, providing access to the data in closer to near real time than has previously been achievable. CSIRO then processes the raw data into level 1 images, and then we distribute those images to the users. So the mission planning that we're undertaking allows us to meet these 3 key objectives. So the first is to support national emergency data needs. So this is collecting data for things like floods, bushfires, and other disasters or security type events. The second is to provide background acquisitions for Australia-wide wall-to-wall mapping, which will enable users to facilitate systematic measurements over the whole country. The third component is then to support different R&D projects for the research community. So that includes universities, SMEs, government, and any other strategic partners. So the key things to note here is that the data that's collected for all of these objectives will be made available free and open access with no proprietary period. The usage of that data is subject to the terms of an end user license agreement, and it cannot be sold. And the new tasking requests for these R&D projects that fall under Objective 3 will be allocated on a merit basis, as I mentioned before. So I'm going to talk to you now a little bit about applying for new Novasar tasking for your R&D projects. So users will be required to submit an application, and this model of accepting applications has been used successfully for the Australia Telescope National Facility for over 10 years. So it's been proven successful for many, many years. So you will be required to submit applications via an online system called Opal, and this will be on approximately a quarterly basis. The proposals will consist of 4 different elements. So the first of these is a cover sheet that summarizes the researchers and the proposed use of the data. And this is an online form that's contained within the Opal system. The second step is then to complete an acquisitions table, and this contains the imaging requirements. So it tells us which mode you want to use, how long you want the data for, etc. And again, this is an online table contained within the Opal system. The third component is then a more detailed justification. So this justification should include a summary of the project, a summary of the technical feasibility, information about the science excellence or potential for commercialization, the potential for science impact, and the value of the project in building the Australian SAR community or SAR capability. And these are the key assessment criteria that the proposal will be assessed on. The fourth component of the proposal is then an area of interest or AOI file, and this allows us to actually see where you want the data and to use in the mission planning. So who can apply via Opal? Initially, anybody in Australia can apply, and there is scope to extend this to the international community in the near future if the demand allows. A time assignment committee is in place to assess proposals, and anybody who receives data from Novasar through the Opal system will be obligated to join this time assignment committee and help to assess future proposals. There'll also be a sanity check stage by the satellite operation managers to ensure that what is being requested is feasible. The actual imaging time is then allocated by the satellite operation managers at the discretion of the facility director. So what types of requests will be accepted through Opal? Well, it's important to remember that Australia has a 10% share of the Novasar acquisition capacity. Therefore, there is a finite amount of data available and limits upon the amount of data that can be requested for an individual proposal. So for the best chance of having a proposal accepted without any modifications, we recommend that the areas of interest are no wider than the swath width of the selected mode. This is because if you select a very wide area of interest, it requires consecutive days of imaging, and this uses a disproportionate portion of the satellite capacity share. It's also useful if AOIs are no longer than 400 kilometers in length. And as I mentioned earlier on in the talk, they shouldn't clash with another mission partner's region. So for more information, the operations team will be on hand throughout the application process to provide guidance, to help you select appropriate AOIs, and to help you determine which acquisition mode is best suited to your project. And there's further information on the application process will be made available through our website. So Novasar data is provided in level 1 L1 format, and this includes single look complex products and multi-look detected products. For those of you who are also familiar with analysis ready data formats, We're also in the process of distributing ARD products that are compliant with the CEOS Card for L guidelines. The current software that's compatible with the data includes Gamma and ENVI SARscape, and there are some utilities also available in the European Space Agency's Snap Toolbox. Any updates on this will be provided to users in due course. Currently, the satellite operator SSTL are developing these tools with the European Space Agency. So actually accessing Novasar data will initially occur via an online form shown here on the left. And this allows users to download KML files that shows all of the available data. Clicking on the polygons will then provide a capture ID, and then you simply submit the capture IDs of the images that you require to through an online data order form. Phase 2 will see the launch of the Novasar Data Hub, and this might look quite similar to you because it's actually a tailor-made version of the European Space Agency's DHUS that many people will have already been using to download Copernicus data. Phase 3 will then involve the addition of the ARD products through this data hub. So I mentioned earlier that we've been acquiring data on an increasingly regular basis for almost 12 months. And this data has been collected for a number of purposes. So firstly, for testing out the mission planning software, learning how to task the satellite and how to use up all of our capacity in the most efficient way. And these types of images have been acquired over capital cities, corner reflectors, and other landmarks. We've then been able to capture imagery for some disaster events in Oceania, including flooding in WA, the bushfires that impacted the East Coast earlier this year, Cyclone Harold, which hit the Pacific Islands in April, and the White Island eruption in New Zealand last December. We've also been working towards having a full first background coverage of the whole country. And then through our SAR Science Initiative, we've been looking at some initial science applications as we begin to develop workflows for using Novasar data. So this includes actually acquiring data from multiple SAR frequency bands over regions coincidentally. So here you can see the coverages of the data that we've captured. And you can see that from December, really the density of this coverage starts to significantly increase as we begin to task the satellite in a more effective and efficient way. And actually, up until October this year, we've collected over 750 images. So this is the full coverage of the data that's been collected so far. And this 750 plus images will be made available free and open access to users when the facility opens. So we've, in our sort of development of preliminary workflows, we've been able to use some of this initial data for quality testing and also to begin to look at how we can work with software providers to develop the readers to ingest the data. And this has been undertaken through the SAR Science Initiative, a project that's run under CSIRO's Space Technology Future Science platform. And really this project is intended to support Novasar activities, including the development of key workflows, supporting users to work with the data, to develop how-to guides, and also to carry out some activities to explore the sensor's capabilities. And the intention here is really to develop new Earth observation capabilities and expertise focused around Novasar and other SAR datasets. So a suite of case study applications provide some initial insights from the data and are to be developed into how-to guides for users. And these include mapping bushfire damage with Novasar, looking at crop mapping using multi-frequency SAR over this agricultural region in WA, mapping flooding with SAR and Sentinel-2 data, and also working with the maritime mode to explore how it can be used for the detection of shipping candidates. So to finish up, Australia's 10% share of the Novasar mission is being operated as a national facility. These operations are managed by the CSIRO Centre for Earth Observation and are governed by an independent steering committee. The facility will be launched before the end of 2020. And when this launch happens, it will open up free access to over 750 images that have already been captured. And the usage of that data will then be subject to users agreeing to an end user license agreement. The launch will also involve the opening of the Opal proposal system, where we will be accepting proposals for new tasking over specific areas of interest for your R&D projects. So announcements around the launch of the facility will be made via CSIRO and shared through the EOA communication channels, or you can also register your interest in receiving updates directly via the Novasar info email address. You can also be kept up to date with key information through the Novasar website. So again, these are the main points of communication that you'll need. And I look forward to taking your questions in the discussion session.
Great. Thanks very much, Amy. That was extremely helpful. So what we'll do now is we'll hold questions until the end. And if you do have questions, please type them into the chat window. What I'll do now is if I could ask Greg Madden from GeoImage to share his screen, please, and I'll just do an introduction for Greg. So Greg has over 29 years of experience in commercial and defence geospatial sciences industry, and has a specialist knowledge of both electro-optical and radar imaging systems. He has built a sort of solid experience and reputation on image processing methodologies and project management for large-scale satellite image projects. Recently, Greg's been involved with the production of interferometry projects, and noting that may be a new term for a number of people who are actually listening to this now. And hopefully Greg will talk about what interferometry is, using a whole range of different imaging radar techniques, as well as positioning systems as well. And a lot of this has been done using packages like InvisSarscape and others. So Greg, I can see you've got the slide set up. I'm happy to hand over to you now if you want to turn your video on, and I'll get on mute and get out of the way.
Thanks, Stuart. Good morning and good afternoon to everyone. I've been given a request for a quick presentation on surface movement monitoring and some of the work that the industry is doing in regards to this. Firstly, I'm looking at, if those who don't know, GeoImage is an Australian company. We've been around since 1988. We're independent specialists in satellite data and processing. We have access through our agreements to a number of different radar sensors, and this really gives us great flexibility to be able to conduct projects and to collaborate as well with not only the satellite operators, but also the software producers. And again, because we also deal with high resolution optical imagery, we can use that and to help with the collaboration of projects. And recently, we had very close contacts with surveyors here as well. So we find ourselves positioned to be able to press forward with establishing and developing a surface movement monitoring service, which is typically known as INSAR. We use interferometric synthetic aperture radar, called INSAR because it's easier to say. Typically what we're doing is we are observing, using satellite-based radars to identify surface displacement. They can either be subsidence or uplift, but not only displacement, but also the movement velocity, the rate of change. Because obviously if we've got displacement that's as a ever-increasing, actually increasingly rapid rate of change, it becomes a problem for roads, for mines, for buildings, generally everything. INSAR, we have two components. I won't give a total revisit to radar, because everyone's reasonably comfortable with what radar is, but it has two parts to the signal. Normally, traditional uses, we are looking at the amplitude of the signal, where we're looking at the roughness and the structure, and we get a good visual representation of the lay of the land, and we can conduct all sorts of analysis, a lot of that visual. But we also have a phase component of the signal, and that's on the bottom there. And it doesn't make a lot of sense to anyone except when you start thinking of it measures distance. And the phase is what we use to measure, the phase portion of the signal is what we use to measure how far away the surface is. It's another shot of just the amplitude of radar, just to flush that phase image out of your mind, because it's no good to anyone unless you're using software. If we get to INSAR, have a look at how it works. On the left, we have our pass 1, which is pre-movement of any ground movement, and we can see our phase. It's going from the satellite down to the ground and back, and because it's a known frequency, we are actually able to measure how far that, or the elevation of that ground based on, we know where the satellite is, we know the speed of the signal, and we know the wavelength. When we go past on a second time, post-movement, we see our phase has shifted, because in this case, we've got quite a dramatic drop in the surface in subsidence. We're able to measure, using that change in phase, we're actually able to measure how far the deformation of the landscape is. Because all of a sudden the signal is either closer, or what's returning to the satellite either faster, or taking longer to return, indicating a change in the landscape. If we have a look at a quick a visual, we can show that as a substance happens, the ground is subsiding. We're seeing an increase there, it's highlighted in the red, in the phase, and all of a sudden the signal is longer, taking longer to get back to the satellite. Therefore, the distance between the satellite and the surface has been extended. If we do this once, we can measure the displacement of the feature, either closer or further away from the satellite. And as it goes up and down, it gets closer and further away. And because we're looking at wavelengths, which are typically we're talking centimetres, we start getting highly accurate measurements in our deformation. We're talking millimetres, 5 millimetres up to 15, depending on the wavelength. And all of a sudden, we've got some very high accurate measurements that are starting to pick up on some of the more subtle movements of the landscape. Now, there's a number of ways that we can do this, and it comes down, they call them a variety of different names depending on who's developed them, the approaches and whatnot. But basically, when you get a stack of SAR images, known as interferometric stacking, we can start drawing up a baseline of what's happening with the Earth, and also we can start developing trends as features are subsiding or uplifting. We can do this a couple of different ways. It's not the only ways we can do it. On QImage, we're kind of looking at two specific approaches. We're looking at persistent scatterers, and here we're looking at what are typically scatterers that are always around persistently appearing on the imagery, hence the name. They tend to be man-made features, but they can be natural. This is good for urban areas, and also good because it takes away some of the complications caused by vegetation. Another way is a small baseline method, and that looks more at our natural features, more at surfaces, and looking more at our distributed features on the radar. It is susceptible to changes in the landscape and the ground cover, but it also gives a slightly different response. So often we use them hand in hand. What the products actually look like. On the top there, we have an example of persistent scatter interferometry. We've got the velocity there. Typically, we measure these things, this deformation, either in displacement of millimetres or velocity in millimetres per year. On the bottom, we've got a short baseline surface coverage. So, see on the top, all those individual dots are persistent scatterers, their features. They're sitting on the ground, and normally we can measure the deformation of the surface by their movements. So have a look at a case study. If we have a look at one that's happened here in Australia recently, we can see what can happen, and we have a look at could we have foreseen particular event, anyone who may know about the Cadia gold mine in New South Wales had a bit of a mishap a couple of years ago. The gold mine's located just outside of Orange in New South Wales, and is the operator of the second largest open cut mine in Australia. It has two large tailings storage facilities. There's a northern and a southern facility. And in January 2018, works began to increase the capacity of the embankment of the northern tailings storage facility by raising the embankment wall. In March 2018, they stopped production because they had a partial collapse of this embankment. There's all sorts of reports out as to what caused it. Find those online, but what we're looking at in particular, this could be a foreseen a partial collapse, using interferometry. We have a look at a time series of Sentinel-1 radar captures, starting from January 2018, and we're scrolling through February, 25th of February is the last, and the 9th of March, we have a partial collapse there of the embankment, which has come up really well on the Sentinel imagery. And then as an optical, because quite often we like to use optical in hand with radar, so we get a comfortable view of what's going on. We have here some imagery taken more recently of the embankment area, and we can see that the embankment has collapsed, tailings have spilled out, fortunately contained within the southern tailings storage facility, but nonetheless it did cause a problem for the mine operator. Could we have, would surface monitoring have given us any heads up to send any alerts out and see whether we could know what's coming up, what's happening? We have here is a study done using Sentinel-1 data. It's 20 metres resolution product, and we used 35 scenes to create a baseline of what was happening on the surface there, and we can see the movement in red right in that circled area, and that is right where the mine operator was doing work on the embankment. We could see up in the top corner around January, 1 month before the event, we actually see an increase in velocity of the displacement. Tailings mines, they're made of earth, they do settle. The tailings in there do settle as well, because it's the nature of the storage area and the way it works. So they go in as a slurry and it dries off. But when we see a rapid acceleration of subsidence, that's a heads up if there's a problem. We go and have a closer look right into in this case, the vectors derived from this small baseline. You can actually see many little interrogation areas there on the graph, a rapid drop-off as we get closer to the February 25th, which was the last scene before the collapse of the embankment. This rapid acceleration gives an alert that something is not good in that area, especially for the engineers that are working. Going back, in hindsight, which is wonderful, a monitoring service would have been able to assist and raise the alert that something wasn't correct and there was problems in the work that they were doing there on the embankment. It's not just the mining sector that there is use for surface monitoring. We can also look at lines of communication with roads, rail, look at urban areas. This is an area in Germany using TerraSAR-X, which is a high resolution pixel. There's 34 scenes there. We can see subsidence there and surface movement of the roads in areas and also the ground. What's happened there is they started up a surface mine in the area that was mining lignite, which is brown coal. And as you can see, as it's been ripping away at the earth, we've got some subsidence there in the local area, which in this particular case, the operator who wanted the study done is highlighting just what's going on. You can see that some areas northern half of the image are quite stable, and all that red is minus 20 millimetres subsidence, and that's a year. So there's a pretty rapid acceleration of subsidence. We don't need to look at, we can look at the surface of the Earth. This is the Burgan oil field in Kuwait, just south of Kuwait City. This is an area where there's Terrasat X scenes available, and a stack of 30 scenes has been used to conduct the surface monitoring with INSAR study, and we could see that there is some subsidence there in the middle of the oil field as a result of the production as they've opened up. You can see to the top half, it's all very stable, but very localised in the southern area part of the oil field. We have a vertical movement velocity of down around the 5 to 10 millimetres per year. Those are very stable areas surrounding it. So it gives an idea that there is subsidence going on, which may or may not be problematic. I think the idea is that you're aware of what's happening, and the surface monitoring will allow that to do that. And it does it because it's remotely sensed. The benefits of using the radar, it's obviously like everything, it's remotely sensed. We don't need to be on the ground to do it. With the radar sensors that are running around nowadays that are available, whether you pay for them or they're freely available through Sentinel, there are very high revisit rates, which is important for interferometry because you want to have as many closely spaced images as possible so you can reduce the ground cover changes. There's no infrastructure required on site for the mine, so we don't need, in this case, we don't need sensors, unless we've got reflectors, that's a bit different, but we don't need prisms, we don't need sensors, engineering sensors on site. It's highly accurate results with the product. We get down to the millimetres, which is good. It's handy when we're looking at the Earth deformation. With millimetres, but also we can analyse the velocity of the change as well. Being a satellite image, we get large areas captured in a single overpass. This means we can look at the whole site, not just portions of tailings facilities, dams, or portions of highways. We're looking at a large area that we can conduct the analysis on. It's also great for remote areas as well, which we know is the benefit of the remote sensing. We don't need to mobilise out into the areas to which is UAV or LiDAR. It's a satellite image, and it has the benefits of being able to work with those areas. So that's a quick demonstration on what we're doing here at GeoImage and the affiliations and collaborations we're working with. Surface Movement. I look forward to questions later on. Thanks for listening. Back to you, Stuart.
Excellent. Thanks very much, Greg. And again, I actually do want to acknowledge GeoImage as probably one of the longest running commercial Earth observation companies in the world, actually. So it's great to have them presenting today as well. All right, so again, if you've got questions, please type them into the chat window. We'll come back to them in the discussion section. We'll move on to our next presentation is Professor Lin Lin Ji from University of New South Wales. Lin Lin, if you're able to share your screen, I'll just do an introduction while you get the screen in share mode. So Lin Lin's a Professor of Remote Sensing and Earth Observation in the School of Civil and Environmental Engineering at University of New South Wales. He's been studying Earth observation since 1985. His research group's had a number of awards for the type of work that they've done, particularly to support disasters like the Sichuan earthquake. This was awarded one of the Asia Pacific Spatial Excellence Awards in 2008, and he was New South Wales Scientist of the Year in 2009. He has his PhD from UNSW and his Masters and Bachelors of Engineering is from Wuhan Technical University of Surveying and Mapping in China. He also was a postdoc in the Meteorological Research Institute of the Japanese Meteorological Agency. I think a number of you know they're one of our major partners in Earth observation, particularly for geostationary imaging work. Lin Lin's also a foundation member of the Surveying and Spatial Sciences Institute, as well as being a member of the Institute for Electrical and Electronic Engineers, life member of the American Geophysical Union, and he's been and is currently a principal investigator on a number of radar-related Earth observation missions. So, Lin, I'll hand it over to you. Thank you.
Thank you, Stuart, for the introduction, and good afternoon, everyone. I want to just basically show some of our case studies, start from bushfire and then flood and earthquake, about a couple of case studies for each. I don't need to repeat a lot of details about the Black Saturday bushfire back in 2009. The obvious is one of the worst events happened. Something I did want to highlight is about the period. It's more than a month. And then, of course, a very good number of fires, 400 fires, So the other thing I want to touch is area. It's 4,500 kilometers square. Well, my bottom line is, you don't really have that capability just to do it from airborne. You have to use satellite. So that's the bottom line here. I want to just share this result with you. Obviously, from the right-hand side, you might be able to see this little dot over there, small spot fire that we can pick up. And then in the middle over here, a quick comparison between Beechworth and the Dargle. For experienced people, this one has been contained. That one is still out of control. Very obvious. This is the beauty of satellite imagery. And by the way, this is shortwave infrared. Something that perhaps not that obvious is we need to look at here. We know that Kinglake and Marysville and places like that were actually the epicenter of the Black Saturday fire, but unfortunately, guess what? It's actually under cloud cover. Initially, when I had this result, I thought it might be a thick smoke, but I was proven wrong, so it's cloud. In the gap here, you do see the fire down there. So in that sense, whether you agree or not, the shortwave infrared was a kind of failed, really, at that moment. But that doesn't stop us from speculating. Academics, we love doing that. So I've been around to many agencies talking about, if we do have real-time access to satellite information, we really should go proactive. We have this very powerful firefighting devices, such as here, not to mention the fixed wing air bombs and stuff like that. So if you do have intelligence, accurate intelligence, then you can actually get rid of the fires before they develop to major fire fields. These are obviously multi-temporal results. As you can tell, the fire spread, as I mentioned, unfortunately, we don't really get a comprehensive picture thanks to the cloud cover and stuff like that. I want to zoom in a little further as well, just on 3 areas that indicated over here. Each is unique. So looking at the epicenter, as I said, the Marysville Kinglake. In the middle, we know that it's decimated, but we don't have any information. Again, the cloud cover that's got us, unfortunately. Then look at the Beechworth. So when we started, we got a full coverage. We were lucky because there was no cloud cover over there, but later on, cloud also became a problem. This one worth a little further look. So you might have noticed some places the fire actually were on the water. So initially when I had the result, I actually told my assistants there might be something wrong. They need to go back and redo their results. And then they came back to me and said, well, everything has been done and it's like that. And why is that? Okay. Well, coincidence, isn't it? Very similar to a title that Amy put up. Why here, why now? And you say, well, this is a radar session, and you've spent quite a few minutes talking about shortwave infrared. Well, of course, we're focusing on temperature difference. There's no problem with that. It is fire, but we do have 2 major challenges over here. One is cloud cover. The other is actually the hot air balloon. Balloon, as I indicated in the last animation, that could potentially mislead us in terms of where the fire was and so on. So we actually have been doing a lot of research and indeed to try to convince a lot of people we need a brand new approach to fire monitoring, bush fire, because it's not just fire. You need not to only look at the fire aspect, but also the bush aspect as well. And of course, many of us know that radar is a wonderful technology when it comes to bush monitoring, okay? And of course, as earlier speakers touched already, I don't intend to speculate on that. It's all weather, it's day and night, and hence potentially, of course, new missions in the next few years. Temporal resolution is no longer a problem. So what we look at the UNSW is a very unique way. We look at the byproduct of the InSAR process, the coherence. So basically that's a similarity between two images, one image collected before the event and the other after. Most recently, we actually had a sort of accident, if you like, hazard reduction burning out of control. It's 10th of October, just a few weeks ago. And of course, you can tell the impact over here. And of course, the traffic, it doesn't matter whether it's road traffic and rail traffic, have to put on hold. For those who are not familiar with the location, it's a waterfall station in the middle of the national park, really. Okay, still start from something we're familiar with. The true color, tell you the smoke, the burnt scar. That's about it. The shortwave infrared is actually doing a brilliant job when you don't have cloud cover, okay? So you can tell the upper part contained, the lower part out of control. And of course, the hazard reduction really was just intended to be around here, okay? So that's what we are good at, I hope. So we actually pull out some archive images, formed a pre-event pair. So both the first image and second image acquired before the event, as you can tell. We have one mid-September, the other end of September. This co-event pair, as we call it, one was collected before the event and the other as the fire is going. As I said, from the image collection perspective, we were kind of lucky because on the day when the event happened, we actually had a SAR, imaging SAR collection, okay? So that is a brilliant data set for the research. We actually went further to do some further analysis so that we can highlight the area that has been destroyed. So as I said, that's very much a bush being destroyed and hence highlighted by our sort of innovative technology, if you like. If you compare with the shortwave infrared over here, that's this part that we're talking about. And obviously there is a 1 day difference between the two. So the optical was captured 1 day after the SAR, and hence this speed, well, actually not in there. It didn't occur yet, okay? So in that sense, it was spot on, and hence I'm actually quite excited in terms of going that further on this track. It's still work in progress. Ideally, we have the end product. It's just a shapefile to indicate a far field or otherwise a small spot fire picked up about by the coherence difference, all right? Okay, back to the radar. So we did have reasonable track record of research in this area. So back in 2011, we obviously used the InSAR coherence to monitor extensive floods in Queensland as well. This is the Rockhampton result promoted by the BBC, as you can tell over there. At that time, we were fortunate to partner with the Italian Space Agency, so they actually lent us a mobile ground receiving station. We placed them in Bathurst. We demonstrate that you know, when you get hold of the hardware, you can actually minimize the delay. So from image capture to flood intelligence on the website, 29 minutes, less than half an hour. There you go. The Nepal earthquake, I just want to share with you the results very quickly. So in a sense, it's not massive. So we managed to capture it just in one single frame of the image, which is good. And of course, what has been quite significant as far as we're concerned is we're not just happy to get the results and perhaps to write a couple of papers on that. Really kind of step into the shoes and indeed see things from the perspective of the local residents and say, well, what could the result do to help them, really? So what we did is actually look at events of similar magnitude and perhaps similar geological settings and so forth, and say, well, there is actually something not so great that is going on here, because obviously the expected displacement is should be much more than that. It should be more than 3 meters. But what we measured using the radar, using InSight, is just about less than half of that. So we look at other case studies, and indeed we managed to do a kind of forecast really on the possibility of major aftershocks and so forth. And of course, we did our homework, make sure that our calculation is okay, our the conclusions is not going too far and so on. So we managed to publicize that both here in Australia, but also overseas as well. And guess what? It was spot on. So we managed to publish those on 5th of May, 6th of May, and then 10th of May. And the major aftershocks happened on 12th of May. So that's an example of what you can do in terms of when you have access to some high quality data and stuff like that. Obviously, we also send the results to relevant agencies, as you can tell over here, in Nepal, in China, in other parts of the world. Just very quickly, a comparison, obviously the Nepal quake, the seismic fault is reasonably small, and hence we can capture it with just a single frame of image. This massive quake happened in China back in 2008. That's where we actually started this journey of near real-time mapping of natural disasters. Unfortunately, the seismic fault was massive. It's more than 400 kilometers in length. And also the imaging mode, as you can tell over there, doesn't help us. You know why? The single strip by the Japanese satellite is almost perpendicular to that seismic fault. And hence, every time you've only got a small chunk of it, 70 kilometers to be exact. So it actually takes 7 paths in order to capture the whole area. The European Space Agency satellite is much better because it's operating in the ScanSat mode, and hence a single image covers this whole seismic fault. So again, it's an exciting journey. It's something that I'm very keen to work with a range of partners. Some of you must be in the audience. So if you have some sort of applications similar to what I've just mentioned, we're more than happy to work with you and indeed perhaps demonstrate again and again the potential of radar interferometry in particular. The last thing I want to touch today is for many years now, we have been running our fully automated system, 2 systems. One is obviously targeting the differential InSight, and the other is the time series InSight, the persistent scattering InSight Greg just mentioned. I also want to take this opportunity to thank my generations of students and postdoc researchers, and my former colleagues, and also overseas partners as well. So looking forward to working with you all in this exciting area of radar interferometry. Thank you for listening.
Excellent. Thanks very much, Lyndon. That really covered a broad area there. If I could just get you to stop sharing your screen for the moment, that'd be awesome. Okay, so first of all, I do want to again thank Amy, Greg, and Lyndon for giving us a really good overview. A couple of things there. This is an area in terms of imaging radar collection that has been around for a little while, but our ability to access and process these data sets has not been as widespread as optical image data sets in a number of areas. I do also want to acknowledge that there are substantial applications for physical oceanography that we haven't really covered today, and that's something that we'll try and do more of in future. Amy covered it a little bit in terms of ship detection, but actually, ocean surface height, waves, those sorts of things. We do have a lot of work going on there too. So just in terms of going forward a little bit, I think, Amy, thanks very much for answering those questions that were in the chat window, so they'll be kept with the recording. If there are any other questions, I'll get people to type them into the chat window and we'll go through them. I think I do want to pose a question to the panel for everyone to think about. And there's a little bit of background to it. So the background is, we do have some archive imaging radar data sets that's open access and I guess public good, so Sentinel-1. We can access that through global data stores, whether it's through ESA stores or Google Earth Engine has also Sentinel-1. We're starting to see new commercial satellite imaging companies like ICEYE and Capella Space come on board, and I'll put the links for those up soon. Where does everyone who spoke see the next 5 years going in terms of access to radar imagery, number one, and then the type of products we can produce from it? Might just start with Amy first, and then I'll go to Greg and Lynn.
Sure. So I think what's interesting with these commercial satellite constellations is that for the first time they will be providing basically hypertemporal SAR data. So we'll be getting SAR data at, I think, sort of up to 90-minute intervals. Once that's what's proposed with these full constellations. And I think that really, we don't know how much the Earth is changing at that that temporal frequency. So what that will show us, I think, is pretty interesting, balanced by the fact that if you're getting a piece of data every 90 minutes and you have to pay for it, your bill suddenly gets very high very, very quickly. But the cost of these commercial data sets is decreasing with things like ICEYE. So it's opening up the access a little bit more. I think they also seem to be quite on board with science and R&D type applications. And then the other thing is that the major space agencies, ESA, NASA, will be launching a number of new SAR missions at L-band. And previously our L-band data has been about every 46 days. It's not that frequent. It's been a little bit limited, but we recognize that it's a very powerful data set because it can penetrate so much through vegetation. So I think that a lot's going to come from these new L-band missions. And then, of course, P-band, which is the even longer wavelength, coming from the biomass mission. And, a lot of people are very excited about that. And like Novasar operating at S-band, it's a new wavelength. So I think there'll be a lot of opportunities that come from P-band. So expect to be saturated with SAR data in the next 5 years is the answer.
Cool. Well, thanks very much, Amy. I'll just switch over to Greg now in terms of thoughts for the next 3 to 5 years on what's likely to happen and building on what Amy said.
I think, like Amy just said, that there's a lot of good information coming. It's very exciting with the freely available research satellites that are going online, some of the commercial vendor satellites that are going online, both in the optical and also the radar. And I think it's just going to be swamped with more and more data. There's some microsats going up. Look, it's just exciting, and it's going to allow us to do much more work through the different bands, and of course the different revisit rates will certainly help meet a few extra needs in the general public. So it's exciting times. It's a good time to be around.
Thanks, Greg. Over to Lynn for your thoughts future-wise.
So very much I share Greg and perhaps Amy's excitement around this. Perhaps I start from the Sentinel-1A and 1B. I must say I'm very pleasantly surprised by European Space Agency, how they manage the twin satellites. So, as Amy put it, the earlier missions, you have to wait for more than a month for an update. But with Sentinel-1A, 1B, a single satellite once every 12 days. And if you have access to both the satellites, once every 6 days. So it's already sub-weekly. A quick point I want to add is also, let's not just look at the big space agencies, NASA and ESA and JAXA and players like that, but also look in the private sector space. Think about, the amazing things SpaceX has done. So again, I guess in the near future, I'm talking about the next 2-3 years, everyone will be just like me, pleasantly surprised how quickly the SAR satellite deployment has been accelerated because of commercial space activities and so forth. And of course, small satellites such as NOVASAR. So I will stop there. Yeah.
Thanks very much, Lin. Just before we get to some other questions there, I want to pose another question for discussion. And this is an overarching Earth observation problem that's gone on for 40 or 50 years, which is, we just talked about, there's all this awesome data happening, but the people who are actually willing to pay for things in government, industry, defence, want information. I guess I'll put one point of view, which is devil's advocate. Imaging radar, in a lot of cases, has an image or reputation challenge in that it's too hard, too difficult, it's fuzzy, I can't understand it, blah, blah. How do we move to the discussion to, okay, and I think Lin's example with looking at the fire scar mapping, which is, there's work going on fire severity mapping now using radar as well. How do we shift the discussion to, well, look, it's these new products where you've got, information on environmental structure, and it doesn't matter about the radar and the tech behind it, but look, we've got this new information. How do we bridge that gap without going, well, we've got all these new data sets, which is super important from our point of view as producers. I don't know the answer to that question. It's one of the key things that Earth Observation Australia faces for our community, which is, how do we stop talking about all the awesome techo stuff and be like, oh, these are going to solve problems and people can use it in their decision systems, whether you're government, industry, defence. So I guess I'll open that up to, Amy, Greg or Lin in terms of thoughts on how do we present, communicate the solutions that pull along imaging radar.
I think it's a good point, Stuart. And, I always think of myself as a SAR person, and you kind of pigeonhole yourself by the technology you're using. But actually, really, I suppose you want to define the problem from the other end, which is to identify the information gap and pose the technology in that framework rather than kind of being a technology push, actually solving it, beginning to solve the problem by defining the problem. Yeah, I think that's actually a really good point and something that I've definitely been guilty of through enthusiasm for SAR.
And we need that enthusiasm to, I think all of us have that for seeing and getting this working, doing the work on the ground or the water to make it work. So that's a good point to look for the gap. I don't know, Greg and Lin, any thoughts as well?
Thanks, Stuart. I think one of the challenges, or one of the aims that we have here at GeoImage is to actually incorporate the data and the results and package it up into a service to our clients, if you like, which means they're not actually looking at the imagery, they're not looking at the results, but they're seeing the analysis, the reports that come out for the service that's being provided, and it links into their systems, their networks, if you like, in information systems, and stop talking about the technical data, although it's extremely important, but talking more on the results. That helps a lot of the education.
I think that's a really good point, Greg, in terms of you're delivering something as a product or service. It's got, and a lot of our work is how do you build the expertise to deliver that. provide a product or service that fits into the workflow of the government agency or the industry or whoever's using it. I mean, ideally it has to have the science and research behind it. And that science and research doesn't just, it's not something that universities or research institutions do alone. A lot of our private companies do this, our government agencies do it, parts of defence do it as well. So that's something to pull together. I'll just head to Lin now for thoughts on, you gave some really good examples of here are some solutions to problems. How do we communicate that more effectively going forwards?
Well, both Amy and Greg and yourself have well said about, something that perhaps we need to think about as very natural. I was in discussion yesterday with our rural fire services colleagues. Something immediately they can point me to was say, well, it sounds like there is a very clear gap in terms of our research, what researchers can do, and what has been used for operations and things like that. I said, well, this is perfectly normal. Otherwise, still myself and people like academics, we're not doing our job, researchers. We just explore and make sure that we're ahead of the industry on that. So having said that, I do say there's a huge task on us as researchers. Once we have demonstrated that it's feasible, and obviously we don't just do it once, we do it multiple times. We don't just do it for one natural disaster, we do it on a range of disasters. Then we need to get out. It is tough, I have to say. Think about back in 2008, 2009, that was more than 10 years ago. And I'm not just gave it a go and then taking a 10-year nap and that's about it. It's not. So it takes a lot of effort to convince people, but as you can tell, I still got a very positive feeling about, the real world do need the technology. There's no doubt about that. There's no need to be guilty about promoting SAR here. But then on the other hand, we need to recognize it takes time. Sometimes it takes opportunities like we have today. We got 10% of the Nova SAR. I could never dream about that, as a student in Australia. There are, of course, the private sector opportunities, as I said, and so forth. And of course, the very much operational Sentinel-1A and 1B. I just want to give them more credit, put a positive spin very much on what we're discussing now. Thanks.
Thanks, Lin. I think we should also acknowledge that Geoscience Australia has played a critical role with accessing Sentinel data through the Copernicus Hub agreement, which has been established with European Space Agency and the groups there as well. And unfortunately, they couldn't present today, but that's something that we will come back to a little bit later on. So I'm just going to go to some of the questions in the chat in a second, but I think what we've just said highlights, the role, for a community to take in presenting what the capabilities and possibilities are for these particular technologies and solutions, and provide resources for people to access them. And the NovaSAR initiative, and there's also the synthetic aperture radar science initiative that Amy's running as well. Those things are meant to build capacity, and we don't immediately have to design, build and launch an imaging radar satellite, but we can do a whole range of things that will lead to our capability to use them. Just coming back to some of the questions in the chat, looks like there's a question there from Arnon Akkad in relation to, are there any recent improvements in imaging radar technology that takes into account moisture, and particularly what, just trying to read a bit more into Arnon's question. If we've got different overpasses with, it's rained on one day and not the other, often it's hard to match things up as well. So I guess that's an open question to the panel there. Is there any improvements there for both collection and pre-processing of imagery for trying to minimise moisture induced variations, given that that's actually a target that some people are after as well. It's not just noise.
Yeah, absolutely, Stuart. I was going to say, I know there are active projects in Data 61 at CSIRO using Sentinel-1 to look at improvements of fuel moisture mapping and modeling. So absolutely looking at the moisture is the target there. But interestingly, we have in some of our Novasar imagery that we collected over the Amazon have seen kind of rainfall events, but no, I mean, looking at improvements in the processing, it's not something that I'm quite so familiar with, but would love to be able to apply them on this particular Novasar image that I can picture in my head, where you can certainly see the effects of the rainfall.
Well, thanks, Amy. Any other, I think Greg, Lin, or actually anyone else on the call, if there's any other comments you want to write in about sort of, I guess, moisture processing examples. I just want to go to the comment, just move away from moisture for a second to Salman's comment. There is that, previous applications have been event-focused infrared imaging radar, partly due to the nature of the acquisition capabilities of radar. But Salman's also noting that there's a need for the longer-term consistent monitoring, provision of geophysical products. So I think Amy actually alluded to that with the production of both. I mean, there's analysis-ready data, but there's also I guess, products which are available and ready for people to start putting into their sort of decision-making streams, whether that's sea surface height, ocean wave, or ocean wind information. I think we're starting to see those things happen, and having data being collected and corrected properly is a key part of that. So Amy, that's the intention with Novasar and I guess also the Sentinel-1 data collections?
Yeah, so with Novasar, that's the motivation behind trying to create these background wall-to-wall systematic maps of the continent. That's really been identified as something that we'd lacked. But of course, with the coverage of Sentinel data, to make these long-term time series, longer-term geophysical studies, the data hasn't necessarily existed to be able to do that with radar. So with Sentinel, we'll have 1A, 1B, then 1C, 1D, and Sentinel-1 next generation. So I think, thinking about having a 20-year time series of consistent radar data for these types of long-term monitoring projects is actually really a reality now. We just have to allow the time to elapse in order to build up the series of data.
Cool. All right. Thanks, Amy. There's a couple of comments in the chat window from Deepak and also Anthea Mitchell, just about moisture and normalization. I guess one of the other aspects, and I'm not sure how, it's just sort of showing lack of knowledge of the imaging radar area. I mean, a lot of our optical image processing techniques, whether it's correction or enhancement or time series, there is a lot of open source code that you can access. I don't know how prevalent that is for imaging radar, whether it's corrections or time series analysis, whether it's for interferometric applications or other applications. I don't know how much I guess open source code there is out there for doing that. I don't know if that's something people want to, I guess, then Greg or Amy, you want to comment on what's out there in that space, or is that something that we could develop more?
My quick comment on that is we don't necessarily have very much on that yet. Obviously, we have separate submissions looking at the soil moisture. So we might use the product to kind of as a correction for InSAR process.
Yeah. So Amy, were you going to say something as well then?
From the interferometric perspective, there are definitely, there's quite extensive open source, code available, usually, for research purposes only, but a lot of the time series analysis, like related to the persistent scatterers that you've seen in some of the presentations, you know, that's all been developed in universities and is all available open source. And there's actually a pretty reliable community online to answer questions in forums and things like that as well. So I'd say that there are definitely resources out there to work with INSAR data, you know, without having to purchase software. And a lot of that's come from JPL and Caltech.
So actually, just following that up a little bit, the resources page for Novasar and that national facility, is that somewhere where you're likely to have links into like the NASA Jet Propulsion Lab code and also other communities?
Yeah, I was going to raise that actually. So we're trying to compile a page of useful resources, acknowledging the fact that a lot of people maybe, you know, would like an introduction to SAR that, you know, that's worthwhile spending their time on. And there are some really excellent online courses that have been developed, things like the EO College Echo Space. So our intention is to put together a set of resources there. The INSAR side of things we hadn't particularly considered putting there because Novasar is not really intended for that type of application, but it sounds like it could be a worthwhile thing. You know, it's not a huge amount of material.
So I guess my next point partly addresses Paul Nugent's question in the chat window there, which is, I guess if you could put those things on that website, that's a nice national focus point for that, for the community and for what you're trying to achieve with it as well. Are you actually able to post the URL or the web address to that resources page? That's number one. And then the second thing is there a rough date for when things would become, sorry, when I say like the Opal system and all the other things would become active?
Yeah, so we're hoping that will be prior to the Australian Space Forum, if not certainly by the end of before everybody goes on leave for summer break.
Yeah. So the Australian Space Forum is in 2 weeks, I think. And just a reminder to everybody, I'll put a link up for it in a minute. You can attend that virtually. It is in Adelaide if you do want to get along to it. So if you're in South Australia, please head along to it. Otherwise, definitely worthwhile attending for updates on Earth observation. Just being mindful of time and that we are getting to the close of things. I just want to try and draw things together now. First of all, I do really want to thank Amy, Greg and Lin for their presentations today and pushing us even further to building Australia's capability in imaging radar. So there'll be a recording from today where you can look at the slides there as well. In terms of going forward from now, a couple of things. Larissa's actually, if you look in the chat window, there's 2 important links. The first one that Amy's posted is the growing list of resources on the CSIRO's Novasar page is one. And then Larissa's kindly posted the link to the upcoming Australian Space Forum event, which will be 2 days in Adelaide in 2 weeks' time. And then while we're talking about events, I do want to remind everybody that in August next year, we will be having our face-to-face inaugural Advancing Earth Observation Forum. Ideally, there will be a significant imaging radar component to that. So please keep that in your calendars for next year. Look for some more material coming out soon. If you're not on the email list for that, visit the website, which is www.earthobsforum.org, and participate in that. With that, I will close things off for today. Again, thank you to our presenters. Thanks to everybody who attended. We had over 60 people online across the country. It was excellent. And again, thank you to Larissa Marfan, Sylvia Michael and Joe Edkins for making this happen on the Earth Observation Australia Incorporated point of view. So with that, I will stop the meeting, and thanks everybody again for your time, and we look forward to catching up soon, maybe at the Australian Space Forum or at our next Earth Observation Australia meeting as well. So thanks everyone.